Alright, so here we are for another live stream. Today we are starting to look at some geometric representations of x squared, and x cubed, and then we're going to look at adding, subtracting polynomials. We've kind of talked about these throughout the course of the semester. Now we're kind of just formalizing them and putting everything together into a general concepts that hopefully are going to be a little more understandable, because they're things that we've applied, and then they'll be useful as you move into further math courses. So I want to get started with the concepts of these geometric representations. And so a lot of times what we do is we think of a line of any length, so just some arbitrary length, we call it x. And so if we think of working with these letters and variables in equations, just a line would be just the plain variable x. It doesn't have to be x, it could be y, it could be p, it could be w, it could be happy face, it could be a picture of a unicorn, as long as it's something that illustrates that it's an unknown value. And so if x represents a line, we then can take a square, and I'll try and draw relatively square here, about right there, I'm going to say. So there's my square. And if you think of x as the length of a line, then when we're working with a square, we often think of the concept of area. And so the area of this square, it's going to be, x by x, length x and length x, or the area is x squared. So that term squared, when we have something to the power of 2, that actually comes from that physical representation of it being a square. And so when we're working with things like x squared versus x, we're going from the length of a line to the area of a square. And then when we step it even further into 3 dimensions, so we have ourselves a cube in that case. In the case of a cube, what we have is a length of x, a width of x, and a height of x, or a depth of x. But the volume of that cube is x cubed. Sorry, x cubed. So we have x cubed as our volume. So when we talk about cube, that term again comes from the actual visualization of a cube. Now, we don't have anything for x to the 4, x to the 5, or higher powers, because we can't visualize anything beyond that. So we can't draw a 4-dimensional shape. If I stretch this in any way, I pull one of these sides longer, whatnot, other than just getting a skewed cube, I still have a 3-dimensional shape. There is no 4th-dimensional terminology that we have that makes sense. There's a hypercube and things like that, but actually taking x squared and x cubed, those terms again come from, and squared and cube come from that shape. So those are important things to note. So whenever you hear the term x squared, you should think of square. And we talked about that with the Pythagorean theorem as well. You draw a square on each side of the triangle, and the 2 shorter legs, if you take all the squares that make up it, they will make up the larger square. So that's the general concept here. And then just some basic operations with them. So if we take a look at the problems in this section, we are looking at questions number 1, 2, 4, 5, 6, 8, and 9. A lot of these are relatively quick questions to look at, so we're going to probably take a look at most of them quickly, just to kind of get that concept there, and then we'll spend a little more time on the adding and subtracting of the polynomials, which is, again, something that we've kind of done a little bit of that thinking, and so hopefully it won't be too hard to jump into. So if we start off with some of these questions here, so we're looking at question number 1 for each rectangle shown. Write expressions for the perimeter and the area. So the perimeter, remember, is 2 times the length plus 2 times the width. And so what we're doing in the case of question A is we have 2 times, and the length here is 4x, and then the width is 2x. So we can take our perimeter formula and replace the length with 4x and the width with 2x. And so I've replaced those values in there, and now I can actually expand these out. So what happens is we have replace these in the brackets, and I've suggested that along the way. It helps out to make sure that we know we're doing some multiplying here. So we have 2 times 4 times x. So this could actually be written out as 2 times 4. And remember, this is just a mathematical dot, means times. That should be a 4, not a 2. 2 times 4 times x, and then plus 2 times 2 times x. Well, 2 times 4 is 8, so we have 8 times x here, and then we have 2 times 2, which is 4 x's here. So we have 8 x's, and then we have another 4 x's. So that would be an expression for that. And we're probably jumping a little ahead because the next couple sections will take this portion here into more detail, and we'll look at this adding, because there's actually 12 x's. So any of these 3 here, or 4 here, would be a representation of the perimeter of that shape. And then again, for area, which is length times width, we would have the length of 4x and the width of 2x. So we're just substituting in those side lengths. In this case, there just happens to be an x included with those side lengths. But we have, again, 4 times x times 2 times x. Well, if we just kind of rearrange that a bit, and we get 4 times 2 and x times x, well, 4 times 2 is 8. And we know from before that when we worked with powers that x times x can be written as x squared. And again, this, or this would all be representations of that area of the square, or rectangle in that case. So again, these latter portions we're going to spend in the next couple sections. We'll spend more time looking at how those actually come about. But those are different possible answers that you could have there, which are probably more than what's in the back of the or in the answer section of the text that I sent. In the case of question number 2, what we have is a cube has a volume of x to the power of 3. And it says, what is the edge length of the cube? Well, for that one, we can go right back to the diagrams that we drew earlier. So here's a cube that's got a volume of x cubed. And so all the side lengths would be simply x, because it's the length times the width times the height, so x times x times x. And that would give us our cube. And then the second portion there had asked about the area of one face of the cube. Well, the one face, so if I cover up that one face there is just going to be a length of x, a height of x. It's just like the square here. It's just going to be a square because the side of a cube is a square. So it's just going to be x times x, or x squared. So pretty straightforward, I feel there. If we continue moving on there, we have question number 4 coming up next. Question number 4 says, which of the following represents a length? And so now we're just looking for the units, because all of them are 25 for the numerical portion. So centimeters cubed, well, cubed we know is a cube. It's a volume. Centimeters squared, so you know we're looking at a square there, or a squared shape. That's an area measurement. The next one, centimeters. Well, that's a length. Right? We measure straight centimeters straight across with a ruler. We can measure centimeters, length of 25. And then the last one is just another square centimeter, so it's another area. So C is our answer for number 4. In the case of number 5, which one represents area? Well, again, looking at the units, it's going to be that centimeters squared. And they've switched up that D portion to be cubic centimeters this time instead of square centimeters, meaning that it's a volume. So B is the answer for number 5. Continuing with these multiple choice type of questions, which one represents a volume? And again, we're just looking for those units. So the centimeters cubed would again be the units that represent volume. We have to have that cubed in there, saying that we're actually measuring that volume again in 25 little cubes that are 1 centimeter by 1 centimeter by 1 centimeter. And those are those little centicubes that you may have used in previous years. The next two here, number 8 and 9. Number 8, again, multiple choice type of question. Which of the following represents the area of the rectangle? So we got a rectangle here. It's got a length of L and a width of W. Area is a multiplication formula, so we got to have some multiplication, and its area is simply length times width. So the answer for 8 is B. In number 9. What it's asking us to do here is draw diagrams of the situations represented and write an algebraic expression. And explain what your variable represents in that case. So if we take a look at these, 9a, the length of a board is 1 meter longer than its width. What is the length of the board? So we got a board, we got a length and a width, so we're looking at a rectangular type of shape. So we can take that 9a and we can draw that out, just a quick little rectangle here. We're not trying to be to scale or anything, just a little rectangle to work with. And so we have a length and a width. And it says the length of a board is 1 meter longer than its width. What is the length of the board? Well, when it says that, it's not expecting us to give a numerical value as an answer because we can't determine that. We don't know what the width is, so we can't add 1 meter to a number and get that. We could represent the width, though, with the W and say that the length is equal to the width plus 1, or 1 meter in this case. But just to get fewer letters, I'd probably just put the plus 1 and then note that it's meters in like a statement. But we have our length is equal to the width plus 1. If then someone told you, okay, well, the width of the board is 1 meter, then you could say, well, then the length is 1 meter plus 1 meter, or 2 meters. So you can use that. Now we've used that formula we've created to determine the length, given that it's 1 meter longer than the width. And so that was for A. In the case of B, we're given that the length of a tablet screen is 1.5 times its width. So again, we're looking at this rectangular type of shape with a tablet screen, and so we want to know the area of the tablet screen. So again, we have this rectangular shape, and the length is 1.5 times its width. So we got a length, we got a width, and so the length in this case is 1.5 times its width. So 1.5, we can use 1.5 times the width, or 1.5 W. And now it wants to know the area. So area being length times width. Well, what we can do is replace the length with 1.5 W. And so we could have area equals 1.5 W in the length portion, and then the width. So I've written that W portion twice. This was the length. This comes from here, and then the width was just still there. And so you could give an area of 1.5 and then w times w, which is w squared. And again, we'll look a little more at this multiplication concept in some of the later ones, but again, we've done this in the past where we've said if we have a w and we multiply it by a w, anything multiplied by itself is that squared. In the case of C, we have a situation where a cooler has a width and a height that are the same and a length that is twice the width. What is the volume of the cooler? So now we are working with a rectangular prism, and so we have something like this. We're going to have a length, a width, and a height, or in this case I believe is what they said, right? Yeah, so length, width, and height. So it said that the width and height are the same. So the width equals the height. They also said that the length is twice the width. So the length is twice the width. And then we want to know the volume. Well, what we have here is volume equals length times width times height. And we have a relationship where we have w, we can replace h with w, and we can replace L with 2W, and we could make a simple equation with one variable is the idea here. So I can do length is 2W, the width is still the width, and then we said we could replace the height with the width. And so we have 2 times W times W times W, or 2 times W cubed. And so this is a way to simplify this. And it's about picking the right, we want to reduce the number of letters that we have. And in this case, when we're working with the variables, a lot of times when we're working with these equations, if we can reduce the number of letters. So by recognizing that we can replace L with something with a W, and we can replace H with something with a W, we can get it down to just having the W as the only letter or variable in the equation. That's what would help out. So that covers the general concepts with geometric representations. Now we want to look at adding and subtracting polynomials. So that is the 7.2 section. And we had 2, 4, 5, 6, and 7. And so if I switch over to those, in question number 2, we're looking at adding up these brackets full of variables and numerical portions. And so when we're working with these, what we want to do is understand the different parts. The x squared is a term. So this x squared right here is a term. The plus 3x, positive 3x, is another term. The negative 1 is another term. So the minus 1 is a negative 1. It's another term. So these are all individual terms in an equation. And terms are separated by plus and minus signs. So it's not 3 and x as two separate terms because they're connected together. It's 3 x's here. So positive 3 x's. So here we have a positive x squared. We have a negative x, or negative 4x, and a positive 2. These are each terms. And what we can do with these is get rid of the brackets and collect the like terms. So to do that, in the first one, if you look at the first set of brackets, what we have is there's nothing in front of the bracket. And you'll see more of what I mean by like what we have to do with things in the front, especially in the next video. So when there's just a plain bracket like that, and I'm going to just switch over to my note here. So when we have this plain bracket like this, we can just get rid of it. It's just used to kind of neaten things up for us. So we have that first set of 3 terms, and we're adding this next set. So because we're adding all these, when we're adding something, then we don't have to worry about the signs. Remember, when we get to subtraction, we have to add the opposite. So we're adding these up. So we have an x squared, a minus 4x, and a plus 2. So now that we've gotten rid of those brackets, we have a bunch of things that are being added and subtracted. What we need to do is collect the like terms, so the things that are similar. And so in this case here, we have an x squared plus another x squared. I'm just going to underline them as I go through them, because we're putting those together, and we call them like because a square is like a square. This x, remember, could represent a line. A square does not the same as line. You add a line to a square, you get a ladle. You don't get a mathematical shape. You'd have like a ladle or something with a line sticking off the side, or I got measuring cups that look like this. It would look something like that. That is not going to work. So we can't add those together. But because we have an x squared and a square, we can add squares together, and we'll get 2x squared when we do those. The next part here, we got a plus 3x and a minus 4x. Those are like, because again, x would represent the length of a line. So we have a plus 3 and a minus 4. That's going to give us a negative 1, so negative 1x. And then finally, we've used up those. We have the minus 1 and the plus 2. Minus 1, plus 2, and we collect those like terms. Negative 1 plus 2 is going to give us a positive 1. So that would simplify down to 2x squared minus 1x plus 1. We can't combine any other pieces because, again, this is a square. We have 2 squares. We're taking away a line, and we just have a number that we're adding, a single one, that doesn't have a shape, a physical representation. So that's our simplification. Now in the next one, b, what b was is x to the power of 3 minus 3x squared minus 4x minus 5. So it's a little longer, but the key difference here is this minus sign that's going to be in the middle of it. And then it's 2x to the 3 plus 7x squared minus 2x plus 3. So in this case, again, we start by getting rid of the brackets, and we can just drop that first one because there's nothing out in front of it. So x cubed minus 3x squared minus 4x minus 5. But now, because there's a subtraction here, we're subtracting this. When we're subtracting something, it means we've got to add their opposites. So we're going to add the opposite of each thing in here, which is going to make each of these switch. So positive 2x cubed is going to become minus 2x cubed. Positive 7x squared is going to become minus 7x squared. Negative 2 is going to become positive 2x. And then positive 3 is going to become negative 3. So we flip them all to their opposites. And now we can collect our like terms. And again, we have the like terms being the cubes, and then the x squareds, and then maybe we'll do a box here, the x's, and then triangle around the number. So those are our like terms. We can collect those. You can do what I did here, the first one, where I rewrote it all side by side and did it, or you can do them where you mark them off step by step. So here I have x cubed minus 2x cubed, so 1 x cubed here, taking away 2, we're going to have a negative 1x cubed. And I just kind of notch those off that I did them. Negative 3 minus 7, going to give me negative 10x squared. Mark those off. Negative 4x plus 2x, going to give me negative 2x. And then negative 5 and negative 3, going to give me negative 8. So you can do it that way as well if you prefer rearranging it and collecting like terms. If you feel that's more conducive to you understanding it, then do that. If it's like this and you want to do it this way, where you just go through and make sure you hit all your like terms. You can do that. The key is that as long as you're getting the correct answers, it doesn't matter which method you use. Now, a few other questions here to take a look at. In the case of number 4, I just want to talk about that one. It's similar to what we were just doing. So in number 4 here, we have write an algebraic expression to represent the perimeter of the triangular box. So remember, perimeter of a triangle is just add up all 3 sides. It, for whatever reason, didn't copy well. This one here is 9x squared. This one here is 3x squared. I don't know why some of these letters were miscopied like that. But these should be in centimeters. The C and the M got merged. So what you're doing there is just like we did in 2a. We're adding this to this, and then this. So you have just 3 of them added together, but it's the same procedure. Whether you're adding 2 things together, 3 things, or 20 things together. If it's added, you just drop the brackets. If there's a subtraction sign in front of any of those brackets, then you switch them over to the negative or the opposite terms. But in this case here, you're just going to add all those up, simplify it down, and once you've simplified it, you'll have that you'll have an x squared portion, an x portion, and then a number. You replace and then you just have an equation, a formula that you can use to actually calculate the perimeter by replacing the x with the number 1, and then in part D, replacing it with the 1.2. In number 5, we have this printing a school yearbook. So we have the cost to print a school yearbook, and then we have the cost to ship the yearbook. So write an expression to represent the total cost of the books, including shipping. So again, the idea here is that we're looking at adding 2 things together. So we have this bracket here, 100 plus 22n, and then we'll add 25 plus 3n to that, and you'll just end up dropping those brackets when you simplify, and then you'll collect the like terms. B should be 125 plus 25n, which is a linear equation, by the way. And then you can simplify that expression to determine the total cost when 600 books are printed. And so we've actually done a question very similar to this at the on the first test, I believe it was, in that we were working with these costs of yearbooks and that, and the number of yearbooks. So it's going to be the same kind of idea that we did there. Now that we have an equation, our 125 plus 25n, we're just going to replace the n with 600, and that'll determine, and then by calculating that, 100 plus 25 times 600 is going to give you the total cost. And then the same thing in D, then 600, we're going to use 475. So again, while this is a new section and we're kind of looking at things a little bit differently, they're not things that we haven't done before, so they do relate back to things we've done in the past. So number 6, I do want to take up because it is the achievement check question, and so you don't have access to that in the back. So in number 6, we have, as part of gym class, students must run around the perimeter of the schoolyard. Write the distance they need to run as an expression in terms of x. And so this is where you want to just be careful, because all those pieces there, the 4 sides, they have an x portion, and they also have that m, and we don't want to get confused. And this happens, I see it happen in senior classes as well, and experienced math people. Is that m another letter, another variable? Because we can have more than one letter. We have our y equals kx plus b type linear equations. We can have more than one letter involved, and so is that a letter? And so you got to recognize that it is spaced away from the equation. So it's 7x minus 3 space m. So in this case, the m means meters. And each of these cases, the m means meters. So we don't need to include it in our addition of the expression. So if I'm going to write out that expression, then what I will have is 7x minus 3, okay, and we can put that in brackets, plus 3x, and so I'll just put each side in brackets at first here, just to make sure that I keep things organized. In this question, it's not going to matter as so much, but if there was some subtraction we had to do, then that could make a difference in our final answer if we didn't put that there. So that'll keep us making sure that we switch signs as we need to. In this case, though, again, they're adding, no need to switch signs. We can just get rid of those brackets. So we have 7x minus 3 plus 3x plus 3x plus 1 plus 6x plus 2. So we can just have all that. And then we just collect like terms, adding them up as we go. So we have 7x plus 3x, which is going to be 10x, plus 3x, which is going to be 13x, plus 6x, which is going to be 19x. And then we have negative 3 plus 1, which is negative 2, plus 2. Negative 2 plus 2 is 0, so 19x plus 0. Or we could just write 19x. We do not need to put the 0 part there. So that would be part B, simplifying that expression. So this is part A, and then we've simplified that expression down for part B. And so that is 19x meters as the distance in this case. And then the last question there is number 7. And in number 7, we got Valua, I hope I'm pronouncing that right, is sewing trim around the edge of a rectangular tablecloth with the dimensions shown. Write an expression for the total length of trim. So here, the question is very similar to the previous one. It's nice that they put the values in brackets this time to separate them from the units. But the one difference here is that we're going to be adding them twice. So if we want the length of trim, so the trim is going to go around the edge. So we have to have 2x plus 1, and there's also another 2x plus 1 here. There's a 3x plus 4 here, and a 3x plus 4 here. So we're actually going to add them up twice. So your equation there, the expression for the total length would, oh, and I didn't switch that over, and I apologize for that. Let me show that again. So again, you have a 3x plus 4 down here, a 3x plus 4 up here, and then a 2x plus 1, and a 2x plus 1. And so now, switching that back over, we have 2x plus 1, and we got to add that twice. And so we just add them all up twice. And again, like the last one, drop your brackets, add up all your x portions, add up all your plain number portions, and then you'll get an answer, which in this case would be 10x. When it's all said and done, just skipping ahead, 10x plus 10. So that is the basics of some of the questions here on adding and subtracting some of the polynomial expressions. The biggest thing to remember is you can only add x's to x's, x squareds to x squareds, x cubes to x cubes, numbers to numbers. So the variables have to be the same, or if there's no variable, then that's something you've done with adding, subtracting in the past, and it's just as you've normally done. But again, you need to make sure the variables are the same, and that includes the exponent portion of the variable to add or subtract them. Next week, we'll take a look at the multiplying a polynomial by a monomial, and Then we have one more after that on just working with solving equations, and we'll be done our year. End's coming soon. Okay, if you guys have any questions along the way, if you want me to help you out with any questions, feel free to send me a message, email Edsby, and I will try and help you out. All right, you guys have a good week.